Today we're going to talk about the second derivative, concavity, and curve sketching. And I think I'm going to break this into two separate videos. The first one dealing just with the concept of concavity and how it relates to the second derivative, and the second video actually putting that to work, applying that to a problem. So let's start with a couple of graphs, or pieces of graphs. When we look at these two curves, we can see that they are both increasing. The function is increasing in both of these. We can say that f is increasing here, which means that the first derivative, f prime, is positive. This also is increasing. The slope is positive. Okay, so f is increasing. And that means that the first derivative, f prime, must be positive. But clearly, we can see that there is a difference between these two curves. Our brain tells us that something different is going on in the two examples. What is that? Well, if we take a look not at just what f is doing, but what the slope is doing, that is, what f prime is doing, we know that it's positive. But if we take a look at the slope, we'll see that the slope is positive here. And as we go from left to right, the slope becomes more positive. That is, the slope itself, represented by f prime, is increasing. F prime is increasing. What that means to us in regards to the second derivative is that the second derivative is positive in this example. So you see, there is a direct analogy here. What the second derivative tells us about the first derivative is analogous to what the first derivative tells us about the function itself. When the first derivative is positive, the function is increasing. When the second derivative is positive, the first derivative is increasing. Now we can see here that something totally different is happening. Here, the slope is very positive and then becomes less positive and actually approaches zero. So the slope here is decreasing. That is, f prime is decreasing. So logically, we can figure that the second derivative here is negative. We have a name for this. When the second derivative is positive, the function f is concave up. When the second derivative is negative, the function is concave down. And you can see that the concavity is in an upward direction here, in a downward direction here. The same things apply whether the function is increasing or decreasing, whether the first derivative is positive or negative. The second derivative is not dependent upon the first derivative. Here we see two examples where the first derivative is negative. The function is decreasing. So we can say here, f decreasing, first derivative negative for both of these. But again, there's a clear difference. Our minds tell us that. Here, the slope. Now, think about this carefully. The slope is increasing because it is getting less negative. right? So the first derivative is actually increasing here. It's going from very negative to slightly negative, and we can see if the trend continued, it would become 0 and then positive. So what we have here is a situation where the slope represented by f prime is increasing. So the second derivative is positive. And again, when the second derivative is positive, the function is concave up. Here, we see that the slope is getting more negative. When it's getting more negative, the slope is decreasing, which means that the second derivative is negative and the function is concave down. Now, what happens in functions frequently is that the concavity will change. Remember, consider the analogy between the first derivative and its increase and decrease of the function and the second derivative and its increase and decrease of the slope. Another analogy is that where the first derivative equals 0, you could have a change. Well, that happens too with the second derivative. And we will be discussing in our next video intervals of concavity and what happens when the concavity changes. That is, when the second derivative changes from positive to negative or from negative to positive. What happens at a point like that? And it's not as easy to see as, say, a maximum or a minimum is here. Clearly we have a local maximum and a local minimum where the first derivative is changing from positive to negative. Here, where the first derivative is changing from negative to positive. But we also have a point in here where the concavity is changing. You can see clearly that we're concave down here, and here that we're concave up. Well, obviously there is a point where that changes. Somewhere around here, the concavity changes. Where that happens, and we'll investigate that in the next video, exactly how to find that. Where that happens, we have what is called a point of inflection, or if you prefer, just an inflection point. Or, as I said, point of inflection is probably more correct, but and this we simply write as a point, x, y. When the concavity changes at a point on the graph where the first derivative is defined, where there is a tangent line, we have a point of inflection. And again, in our next video, we'll work out an entire problem and see that. That's all.